Okay, I would like to thank the organizer of this conference, giving me the opportunity to present this work. Okay, what we basically do here, we relate the quantum SL2R to the dynamical quantum SU2 group. Okay. So, it's not going to. Okay, thank you. So I will start by recalling the definition of quantum SL2R, and from that I will define the double cross product. From that I will define this double cross product, and I will also give the definition of the dynamical quantum SU2 group, and finally I will give the isomorphism of star algebra between this double cross product and the quantum and the dynamical quantum SU2 group. So we start to give the definition of, we start with this Hopf star algebra for QSU2, which is the compact quantum group of star algebra generated by alpha, beta, and gamma satisfying some commutation relation. And we know that it is non-degenerately paired with this Hopf star algebra. We denote by this curly U convolution dual of our algebra A here, or the dual convolution star algebra. And we can just view this curly U as this direct product algebra. And we have the finite part of our curly U that we denote by this U. And we view it as the direct sum of this algebra. Now we define dt, given by this, which is the right coideal star subalgebra of A, which we can identify with one of the Podle sphere. And we define also C, which is this algebra where dp plus here is the intersection of B with the co-unit. And we know that C has a unique structure of a left A module coalgebra. And you can also write by this IT, curly IT, for the dual convolution of CT. Okay, now as we have this U inside curly U, we define the same thing here. We call this I. We call this I inside this curly I, the compact support part of this curly I, which is non-unital star algebra with the dual right A module structure. So this IT is the final support functionals on C. Okay, we can also view this curly I as this direct product algebra, and we view it finite support part as this direct sum algebra. Okay, now here we consider for T, for a parameter T, we consider these elements here. This element BT inside the IT here, with this star structure and the coproduct. And it was shown by Corwinder that this element BT in fact generate the left coideal algebra IT here inside U. And it is also known that the orthogonal dual of this left coideal is in fact this algebra D here. Now we give the definition of our quantum SL2R, which we can just view as the star algebra generated by these two left and right coideal satisfying some interchanging relation, allowing to take the product. So this is what we call Drinfeld double coideal. Okay, now we can just forget about our parameter T here, and we consider this in a more general setting. We consider these three categories. So we consider this category, this category of the Diophobinen module, and this two extra category. We have by Chirvasitu that this left B module is faithful flight, and this right C co-module is faithful co-flight, because C is co-semi-simple. So by Takeuchi, we have this equivalence of categories. So we see from that there exists a one-to-one correspondence between the opinion module, which is category of this, which is this category, and the non-degenerate Drinfeld double coideal module through this correspondence. So we in fact have a left B module here and a right C co-module which are compatible. Okay, it follows that the category of this Drinfeld double module contains the monoidal structure through the identification with this category, as we saw here, this equivalence. So from that, we see that the category of Drinfeld double module contains the monoidal structure through the identification with this category. In a dual point of view, you can see that there exists a correspondence between module of this Drinfeld double module of this Drinfeld double and this category here. This is the category of I by module with the left A module structure. So this is the same as having the left module for this algebra, for this double cross product algebra here. In the analytic setting, there exists also a one-to-one correspondence between star representation of this Drinfeld double and star representation of this double cross product on Hilbert spaces. So we just complete. To get the Hilbert space. Now we give the definition of this double cross product, which is the star algebra generated by I up and A with this commutation relation. We have this first commutation relation, which is the relation between I and I up. We have this, which is the relation between A and I up. Note that it is necessary to have this area, which is the unitary antipode, to have the star structure work here. And also here, we have the relation between I and A. Okay, now we are just going to stop here and recall the definition of the dynamical quantum SU2 group. So for this, we fix X, and we define for this I here, depending on Q and X. We define these functions, tau and W. We consider the version of quantum SU2 introduced by Kenny, where the dynamical quantum group depends on these two parameters, Q and X. So let B be the non-unital star algebra of functions defined on X times X with finite support. We denote this one, YZ, to be the characteristic function on YZ. Okay, and we give this definition. We define our quantum dynamical SU2 as the non-unital star algebra generated by the copy of D, and these elements here, where epsilon and nu are the signs, and this Y and Z are the dynamical parameter. So in our dynamical quantum SU2 group, we have this unitarity condition. This matrix is unitary in the sense that this is satisfied and this also is satisfied. We also have the star structure defined like this, where this W are the defined functions. And we also have this dynamical behavior here. Okay. Now, this allows also the coproduct defined in the multiply algebra of the dynamical quantum SU2 So this delta here is non-unital. And this is how the coproduct is defined. Okay, now we come back to our previous setting. We recall that the spectrum of IB, which is the generator of the coideal IT, is equal to this set here, where T here is the quantum number, as Professor Juncken has explained in his presentation. It follows also that this should be IT here. This follows also that this left coideal here is isomorphic to the star algebra with finite support function in this set. Okay. Now we see that in the spin 1/2 representation, this IB has two eigenvectors, which we denote by psi plus and psi minus, corresponding to these eigenvalues here, A plus 1 and A minus 1. Okay. Now we denote by psi mu y be the eigenvectors of IB at this value, at this eigenvalue here in the spin 1/2 representation. And we consider that our left coideal here has a basis of minimal projection, which we denote by y by 1y here. So 1y here. So 1y here. So 1y here is the eigenvector of IBT at this eigenvalue. And we do the same thing for the I up, and we get this. So now we need, for this case, we denote by 1 yz, which is product where y one, where 1y here is this one, and yz here is the minimal projection here. Okay. Now we give our main result. You see, in fact, that if we choose x equal to q power a with t equal to this, you see that there exists an isomorphism of star algebra between our dynamical quantum SU2 group and this double cross product algebras given by this, where this beta here, this factor beta here is given by this, and this one here is just 1y up and yz, and this u1/2 here is the matrix coefficient of the unitary representation of this A. So this is important because we'll use this to identify representations theory of this one from the representation theory of this algebra. So this is still a work in progress that we hope to finish. And yeah, that's where I will finish.
Any questions? Yeah.
Can you say a bit more what we hear about this dynamical developments? What's the motivation for introducing this?
You mean the motivation of why we use this?
This dynamical contract. What do we care about this? Understand properties and so on?
Yeah, as I said, this will be necessary to identify the representation theory of this one, and also to make the connection between the representation theory of this, which is known, and the representation theory of the quantum SU2 and the quantum SL2R. Yeah. So we are just looking to make the relation between the representation theory of this and the representation theory of this one, and also between the representation theory of this two and the representation theory of quantum SL2R. That was done already.
Okay, well, let's thank the speaker again.
Okay.
We'll start with next